Hi there, Manuel with the fourth installment of particles. Today let's talk about something practical. I want to make particles move along a network of curves. That can be useful in many situations. Imagine modeling blood cells moving through veins or something similar. And we don't want to move the particles along one curve, but we have this interconnected network of curves there that I imported. And we want to make them move along all of these curves at the same time. And to do this, we want to make use of vector fields. So this episode is not only about moving particles, but it is about using vector fields to move your particles around. A very important and useful concept. So let's directly dive in and start. Inside of this object, you find a file node importing these curves that I modeled for you, and they are interconnected. If I lay down an exploded view quickly, you can see that these are individual primitives. So to make them really interconnected, lay down a fuse sub that will make the primitives use the same points. So before we have 149 points, and after the fuse we lost some and have 138. So now let's first create some pipes for the particles to travel through. But particles usually don't like to move in 90-degree angles. So before we move the pipes, let's smooth this out a little. So lay down a subdivide after the fuse, and this will smooth the curves out. And let's say we up the depth to 4 to get nice and smooth rounded curves. Now let's create some tube geometry from the curves. To do so, lay down a circle that we will use as a cross-section, and let's scale it to 0.035. That is the value I used in my example, and then we need a sweep. Connect the circle to the first input and our splines to the second input, and that will create a lot of circles along my splines. But instead we want surfaces, so go to output and change skin output from off to skin unclosed. Make sure to set the circle to polygon, otherwise it won't work. Like this. And now we have a lot of curves. I plan to turn them into a volume to smooth them out even more, but to do so I need closed geometry, and these two curves are open. So let's generate some caps for our geometry. Lay down a caps sub and append it after the sweep. Oh, it does nothing. And that is because the caps node only works with NURBS or with meshes, not with polygons. And the sweep is by default set to output polygons. So if we revisit the sweep and turn off output polygons, the cap node works. Now you get caps. But now we have meshes, not polygons anymore. The difference being that meshes have a certain structure that is important for Houdini to understand its topology better, to be able to do stuff like cap. But that is not a problem, because we can just append a convert and turn all of this into polygons. So after this convert, now we have polygons. And don't bother with the polygons being oriented wrongly, facing inwards, because the VDB doesn't care. Now that we have that, let's append the VDB from polygons to turn everything into a volume. And this is a little coarse, so what if we go down with the voxel size to 0.005? That's better. Now we have a volume of our tubes. And now we can smooth it. VDB smooth SDF, because this is a side distance field, like so, which will smooth out the intersecting areas. And now we want to convert this back to polygons again. So another convert, but this time a convert VDB, append it here, will convert our volume back to polygons. And now we have nice, seamless pipes with seamless intersections that follow our curves. Great, but we want to have a a thickness for our pipes to be able to render them as glass, and we want them to be open here. So first let's care about the thickness. To give them a thickness, just append a poly extrude, append it here, and let's dial in a distance of 0.005, and that will make the tubes bigger. But as we tick output back and go into wireframe mode, we see that now we have two surfaces, an inner surface and an outer surface. So now the tubes have a thickness. And now for making the ends open. I plan to use a Boolean for that, so I have to first create geometry to subtract from this pipe geometry to open up the ends. How can we do this? Well, let's revisit our splines. I want to place a cube on each end of these splines, so wherever these splines are open. And how can I select only the endpoints of the splines? Well, they have a property that they only have one neighbor. A neighbor to a point is a point that is connected by a primitive, and all of these points have at least two neighbors, but the endpoints, they only have one neighbor. I use this to create a group that holds only the endpoints. So let's lay down a group expression and connect it here. And now let's call the group ends, and let's input a little vex expression that is neighbor count of geometry 0 around ptnum, which is the current point. And this neighbor count should be smaller than 2, like so. Don't forget to switch the group type to points, and now you can see that it selects only the endpoints here. You don't need a semicolon in here because this is not a vex program, but it is just a vex expression, so it is meant to be on one line only. That is why the semicolon is added internally automatically. So don't bother with a semicolon here. Now that we have these endpoints, let's create a box and size it down quite a bit to 0.1, and let's use a copy to points to copy the points to these endpoints. At the moment it is copying a lot of boxes, but as soon as we put ends here in the target group, it only creates boxes at the ends, but they are rotated wrongly. So tick off transform using point orientations, and our boxes will all have the same orientation as the world, which is nice in our case. So now it's time to append a bool to our pipe geometry, and as a second input use the boxes, and this gives just the ends, but as soon as we switch the operation from intersect to subtract, we get exactly what we wanted. Now we have open pipes with a thickness. Time to care about the vector volumes. But before we create a volume, we want to add orientation or tangent vectors to our curves, because we need a vector that flows along our curve. So lay down a polyframe. The polyframe is meant to do exactly this. It creates orientation vectors on polygons, and these are polygons. So if you just connect our splines to the polyframe, it creates a normal and a tangent vector called tangent u. We don't need the normal, but we care about the tangent u. Let's quickly visualize this by clicking here on tangent u. Here you have the vectors, and if you go to the visualizer, you can dial down the length of this, and let's show arrow tips like so. And you see, now we have vectors that run along these curves. And the vectors start here at the center curve, and then they run outwards to these ends. That's important too. So what we want to do now is, we want to write these orientations into a vector volume. Why that? We, of course, could create a pop network that looks up the closest position of each particle on these splines and then reads this vector to use as a velocity, but that is quite wasteful because we have to do these lookups all the time. Instead, it's a lot faster and maybe even easier to write this information into a volume. Then we just have to sample the volume, which is cheap, and we get the correct orientation. So let's do that. But to do that, we first need a volume. So lay down a VDB node. A VDB node just creates a VDB, and we have to tell the VDB node which type of VDB to create. At the moment it's set to fog volume, but we want a vector field. And be careful if you go to class, staggered vector field is a very special kind of vector field where the values are set on the boundaries between the voxels. That is not what we want. What we want is other, because it is not a level set, it is not a fog volume, and it is not a staggered vector field, so other. This class tells Houdini operators that work with volumes how to deal with this type of volume. And now for the type, we don't want a float, but we want a vector float. So a vector in each voxel composed of 3 floats. The advantage of VDB with vector volumes is that VDB can directly create one volume holding vectors. With Houdini volumes, you would have 3 scalar volumes that are combined to form a vector. Cool, but how can we make this VDB bigger? Well, here we cannot. Instead, we have to think a little bit about how VDB works internally. VDB is highly optimized, and that means it is not defined everywhere. That is usually referred to as being a sparse volume. So where the values are the same as the background value, the voxels are not activated. They are not active and don't hold values, and this saves a lot of memory. So in our case, we want the VDB to be activated everywhere. So we want to lay down a VDB activate node. Feed in the VDB, and now we can use this VDB activate node to activate all the voxels that we are interested in. And what is the domain that we are interested in? Well, it is the space that is covered by these tubes. So let's lay down a bound sub that creates a bounding box to these splines, and let's go to the padding and dial in 0.1 to make it a little bigger than the space that is filled with tubes, like so. And now let's connect this bound to the VDB activate. Nothing happens, and that is because we have to go to the VDB activate and tell it to use the reference, so the geometry coming in over the second input, to size the VDB. What happens here in reality is not that it is sized, but all the voxels that are inside of this bounding region are activated, giving us a nice VDB. Before we continue, though, let's care about the voxel size. The voxel size is quite large, so let's go down to 0.02 to have more voxels. After the VDB activate, we have 61 by 56 by 61 voxels. Great, that is something we can work with. So now, to fill in the values here, at the moment everything is just 0, let's lay down a volume VOP, and connect the VDB to the first input. But we want to sample our curves, so we have to input the curve somehow into this volume VOP too. So take the output from the polyframe, that is a curve with the tangent U attribute on them, and put it to input 2. Make the volume VOP visible and dive inside. Inside you find this volume outputting density. That is just a default if you are working with fog volumes. In our case, this does not make sense at all. Instead, we want to use a named output. But to do so, we have to give our VDB a name first. At the moment, the name field is empty, and we just put in vel for velocity here. So now we can create a bind export node inside of our volume VOP, call it vel, and it will set the voxel values of the VDB called vel. What exactly do we want to set? We want to find all the points on the curve that are closest to each and every voxel. And then we want to average all the tangent u vectors found on these points together to create the value for the voxel cell. So how can we do this? There are different methods in Houdini, but a highly optimized one is the point cloud method. So lay down a PC open, point cloud open, and it expects a file. That is a geometry holding the points to find. In our case, this is the curves coming in over op input 2. Connect this to the file. And then it needs a sample position. So this is a location to search around. And this is P. Inside of a volume VOP, P refers to the center point of the currently processed voxel. So now we are looking around the center point of the currently processed voxel for points on the curves, and PCOpen will find them. But it does not output them. Instead, it gives us this handle here, which is of type integer. And that is because the information cannot easily be output. PCOpen is meant to work with other PC nodes, like PC filter, point cloud filter. That is the node that we want to use. And it has a handle input. If we connect the output to this input, the PC filter will internally access the data found by PCOpen, all the closest points. If you go to PCOpen, you see that it is looking for 10 closest points in a radius of 0.1 around the center of the voxel. So the PC filter will read attributes from these found points and average them together. By default, it is averaging position, but we want to average tangent u. And now we want to set it to our volume. But be careful, we forgot to switch the type of this bind export node from float to vector, because it is a vector. And now connect this, and immediately you see that we get something. Houdini has a hard time displaying what we have here, because it is trying to visualize the vectors as fog, but at least you see that you have something. How can we see what we have in this volume? Well, there is a node called volume trail. Volume trail. And it can move points through a vector volume, creating trails. And that is very handy to visualize the contents of a vector volume. So let's use this, but for this to work we need points. So let's quickly create points, and there is a nice node called points from volume, which creates a nice lattice of points, but it needs a volume first. So let's quickly create one. ISO offset standard Houdini volume from the bounds. Let's create a fog volume, density 50, and then points from this volume. And if we now connect these points to the volume trail, and as a second input our vector field, this is what you get. Now we have points traveling through the vector field. And you see this is exactly what we were looking for. Now we have a vector volume defining the directions of the curves, just in one volume. Maybe let's go into the volume VOP again and dial down the search radius to 0.5, like so. Not to make them too big. That is exactly what we need. So this is optional. Now we have our vector volume. Time to create some particles and move them through this vector volume. To create particles, let's use a scatter. Scatter, and let's again use our splines and scatter points on them. Let's say 3000. And now they are sitting exactly on the splines, but I want a little volume around the splines, so let's paint a point jitter, connect it here, and let's dial down the scale to 0.03, like so. Nice points around our splines. Now lay down a popnet and connect this to the first input. And now connect the vector volume to the second input, because we want to use the vector volume inside of the popnet too. Make it visible and dive inside. The first thing is that we have to switch the pop source from using scatter onto surfaces to all points, because we don't have any surfaces to scatter. Let's turn off the guide, and here we have our particles. If we press play, nothing happens, because we don't have any forces nor velocity. But we will change this now. To use vector volumes, there's a very nice node called pop advect by volumes. This can read a volume, external volume from SOPs, and use the velocities stored in there to move the particles around. So connect it here between the source first input, and the wire pops into here. Now let's set this up. The velocity source is set to SOP, but we want to use a second context geometry. That is where our volume comes in. The field name is vel, it found that automatically. And the velocity scale is 1, so you can scale all the vectors that it finds in there. And now the advection type is currently set to update force. But if you remember last episode, we not only can modify particles through forces, but we can use velocities too. And as we exactly define the velocities to use, in this case we don't want to update the force but the velocity. Then there is this velocity blend, and that means it is using the old velocity of the particles and then blending in 0.5 of the velocity found in the volume. That is not what we want. We want instead to just use the velocity from the volume, so set this to 1. And if we now press play, see what happens? These particles are rushing along these curves. There are two problems. First, we want to vary these particles in every frame. That is easily done by going to the scatter and just putting a $F expression here in the global seed, such that the seed changes in every frame, like so. And then the particles are not that uniform anymore. And then we want to dial down the velocity scale to 0.2, say, to make them slower. And here you have it. The particles are moving along the curves. Without further ado, without telling each particle which curve to use, the velocity field is taking care of all of that. But they are now accumulating here at the end, because there the velocity field just ends, so no more velocity means no movement anymore. So what if we just kill them there? And we can do this by using a pop kill. And append it here after the advect node. And how can we define where to kill the particles? Well, we can use the bounding option of the pop kill. And let's enable it. Instead of using bounding box, let's use a bounding object. And this makes the SOP pass field accessible. And now we can pick a SOP. Let's make our lives a little easier. What I want to pick is this geometry here with the boxes. So let's quickly append a null. And let's call it out kill boxes. Like so. And if we now go back into our pop network, we can easily pick this geometry, accept, and it shows us that it found it here with a guide. And if we now rewind and press play, you see that the particles get killed once they reach these boxes. Cool. One level up. So now, let's make our pipes visible. At the moment, the particles and the pipes are sitting in the same object. That's not nice, so let's create another null. Append it here, remember, that is our pipe geometry, and call it out pipes. Like so. Now go one level up and create a new geonode. Call it pipes. Dive inside, and inside lay down an object merge. And let's just merge the pipes geometry. Like so. Now the pipes are residing in their own object, and we can switch the display flag to popnet again. And now you see both at the same time, the pipes and the particles moving through the pipes by using a vector volume. But the problem is that they are traveling outside of the pipes too. And that is because the velocity is only approximating these curves. So they are deviating from the curves all the time. So let's think about how to fix this. To fix this, we need a second influence on the particles. We not only need a velocity that is going along the curves, but we somehow need to push them to the curves, to prevent them from deviating too much. And we want to do this with another vector volume. So let's move this business here out of the way. Call this first volume VOP curves val, and let's create another volume VOP. Just connect the same VDB to it, because Houdini works like this. If you branch off like that, the geometry is duplicated. And we need the curves to the second input too. Let's call this center velocity. And let's dive inside. So here we want to find, for every voxel, the closest point on the curve, the really closest point on the primitive, not only one of the points defining the curve, and then we want to create a vector pointing from the voxel to this location. And this gives us a velocity that is going to the curves themselves. We can do that by using the xyz dist function. It expects a geometry, that is up input 2 again, and a position, that is position, and it outputs a primitive number and a prim_uv barycentric vector. To make use of this information, we need a node called prim_uv, primitive attribute. It takes the same file, then connect the primitive number and the barycentric coordinates inside of this primitive. And now you can sample an attribute from this location, and we want to sample p, the position. And now we want to create a vector between the center of the voxel and this position, so lay down a subtract. And subtract tips to tails, first this found position, and from it the center of the voxel. Then again get rid of this and create a bind export, switch it to vector, call it val, because it is named exactly the same as before, and output this here. We can quickly check what we created if we just connect this to our volume trail and make the volume trail visible, and you see now we have a vector volume that has velocities that are going to the curves. And we can make use of this volume by feeding it to the third input of our popnet. Make the popnet visible again, dive inside, and now let's use this. First, let's rename this first poppet vect advect curves. And now let's create a second poppet vect by volumes. Append it here and call it advect center. And you guessed it, the setup is quite similar, but this time we want to use the third context geometry, and we want to update the velocity again, and this time we keep the velocity blend value at 0.5. Now let's see what this gives. Very nice. Let's go one level up to really check. Here are our tubes. And now the particles are not leaving the tubes anymore because they are pushed along the curve, but at the same time they are pushed inwards by the second velocity field. So this is our result. Very cheap moving particles through tubes by using two velocity fields. And the big advantage is that by using velocity fields, you do these calculations inside of the volume VOPs only once, and then you use the information on all of the particles. If you would do these things inside of a pop VOP, inside of the popnet, you would have to calculate the information in each and every frame, which is really wasteful. And at the same time, you can just investigate what's going on in your velocity volumes and debug easier like this. So, velocity volumes, a very versatile tool to drive particles. The possibilities are really endless. You can even use a velocity field generated by a fluid simulation to drive your particles or whatnot, imported data. It is a very basic and versatile tool. Thank you very much for listening. I hope you learned something in this episode, and stay tuned for the next episode of the Particles course.